Okay, we're going to look at an example of the kind of problem where you have to calculate individual abundances for isotopes of elements, similar to what you have to do, what you read about in your textbook, and there were several examples of those. So here we're going to talk about how you solve these kind of problems. So in this question, you're given some isotope information, and you're given the weighted average atomic mass of sulfur, which is on your periodic table. That's what this is. It's my abbreviation for weighted average atomic mass. And the rule is your percent abundances have to add up to 100%, and your fractional abundance, which is just taking this percent and converting it to a decimal, which means divide it by 100. So those have to add up to 1. So the fraction of 100% is a whole 1. So in this question, you're given some information, and I've put it into a table. So this helps me kind of visualize what all this gobbledygook up here says about this particular problem. So you have the isotope notation right here. You have information from the problem, the isotopic mass in atomic mass units for each one of those. So sulfur 32 has this 31.972 isotopic mass, and sulfur 33, sulfur 34, and sulfur 36. And that's just kind of how you read those. When you see this here, you would say sulfur 32. Okay, so this problem, I'm given well, the weighted average, and I'm given abundances for only 2 of them. It said these 2 are the least abundant of the 4. So I'm given this as my percent, which I divided by 100 to convert it to a decimal, and this is my percent, which I divided by 100 to convert that to a decimal. The problem is, with this one, there are 2 abundances that I do not know. So they all have to add up to 1. So if I look at that, well, I've got 2 of the numbers that are part of that 1. I can see what's left over that I have to make those 2 add up to by just subtracting them from 1. So one thing I can do is just say 1.000, or however many zeros I want, I guess, and I can subtract from that 0.00752, and I can subtract from that 0.00011. So I'll just put another 0 on there. Since those are 5 decimal places, I'll just make that 5 decimal places just for the time being. So I've got to subtract that, and I'm going to see what I have left to make those 2 add up to. So I'm just going to say 1 minus 0.00752 minus 0.00011. I left out a 0, or it didn't. There we go. And then I see that that has to be 0.99237. So whatever these 2 end up being, they need to add up to that so that my result is 1. Okay, so the easiest thing to do, the proper way to do this problem, is do not assume that they're equally abundant. So if you make that assumption, you're probably going to be wrong. So you can't just average that and plug in there. Okay, you can't just divide it by 2. So you cannot assume equal abundance. So I'm going to say that that abundance is X, which means that this abundance is whatever this is minus whatever that is, right? So this is X. Whatever, if I want to get to whatever this box equals, it's that minus X. So this, for right now, I'm going to put like this. So I don't know what the X is, but if I can figure it out, then I can figure this out. So I don't want to call it Y, really. I mean, I want to call it this minus X, because if I keep it in terms of X, it'll be a lot easier for me. Okay, so mathematically, the rule is this is a weighted average, kind of like grading stuff where things count different, like tests count different than a quiz, and a quiz counts different percentage than homework or whatever. So they're weighted. So that means that factors in what it's contributing. So these isotopes, this average, this is a weighted average. It counts how much each particular isotope contributes to it. So I can look at that number and it says 32.07, so it's closer to 32 than it is any of the other numbers, than it is to 33, 34, 36. So that tells me that the higher percentage is probably going to be 32. Just by looking at that, I can say, oh well, since it's weighted, most of the atoms of sulfur are sulfur 32 atoms, and then there are some that are higher that contribute to it going over a 32. So mathematically, when you solve this, you start out by saying that the weighted average atomic mass, 32.07, is equal to each isotopic mass times its fractional abundance. Now that's in your notes that I gave you. So and it's also in your textbook. So this number times the abundance in a fractional form, and is converted to a decimal. So this times that plus this times that plus this times that plus this times that all adds up to equal 32.07. So when you're looking at your work here, then you're going to set that up in that way, and it's going to start out looking kind of messy, and then we're going to clean it up to make it look more like something you're used to seeing. So 31.972 times X. So I'm just going to put that, and then I'm going to add to that this times this. So it kind of would be like 32.971 times 0.00752. Okay, plus this times this. Now if you look at that, that's two parts itself. That's like a quantity. So you've got to distribute this to both of those. Okay, so your 33.968 is multiplied by your 0.99237, and then it's multiplied by negative X. So you just say minus, just do that, 33.968X. And then the last one is this times that, which I'm just going to move down here just a little bit to give me a little more room, hopefully. 35.967 times 0.00011. So I need to clean that up just a little bit. I can multiply this out and get a real number. I can multiply that out and get a real number. And I can multiply that out and get an actual number. Also, I can combine, so take a look at that there. I can combine like terms, this and this, because they're both have the x part of them. So I start out, I can say 32.07 equals, combine my x's. So really I just need to subtract this from that. So 31.972 minus 33.968, and I get negative 1.996. So negative 1.996x. Okay, now I'm going to do these components here. So I'm going to do this times that. So move my calculator just a little bit over so I can see my numbers. That's 32.971 times 0.00752, and I get 3 decimal places, 0.248. Okay, now I'm going to do, so I took care of that one, now I'm going to do this one. And I'll move my calculator over this way again. 33.968 times 0.99237, and I get 33. I get 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 sig figs. So 33.709. Plus, and now I'm going to do this one. So I took care of that one. I'm going to do this one. 35.967 times 0.00011, and I get 2 sig figs, which means 0.00. So what was that? 40. So that will round to 40. Okay. Okay. Now, if you look at that, those are all numbers. You can add all that up together. So I'm going to do that. So the 0.248 plus the, I think it was 33, yeah, 33.709 and 0.0040, and I get 33.961. So this is simplified a little bit now. Like that. Okay, so to solve this, I could subtract 33.961 from both sides. So I'm going to start isolating the x and solving for it. So first subtract this from that, from both sides, and then you'll get a little bit of a simplified part. So get my calculator out just again here. Alright, we have 32.07 minus 33.961, and I only get to keep 2 decimal places, so negative 1.89. So I can simplify this a little bit. Negative 1.89 equals negative 1.996x. So that's what that becomes. Now I can divide both sides by this negative 1.996 and I'll have x. So x equals, and I will do that. Well, I can keep my calculator up here. I don't really need to maximize it. So just take that and divide by negative 1.996, and I get x equals 0. I get 3 sig figs. 99. Let's see, 0.947. Okay, so now I know what this is, right? So 0.947. Now to get this one, I just subtract this from that 99237, right? Just like that. So on my calculator, (99237), okay, and minus 0.947, and I get 0.3 decimal places, so 0.45. So this is what that is, right? This is that. So now I figured out what the abundance of each of the other ones was. Now if I want to convert that to a percent, because it does ask for both, then I just multiply my decimal times 100, and I'd say, oh, this is 94.7%, and then this is 4.5%. And then you've solved it. So now you know everything that you needed to complete that table, when you have all the percent abundances. If you add those up, you should check and see if they add up to 100. So we'll do that real quick. We'll look at the percentage part of it, which I don't need to maximize it. So on my calculator, it's probably good. I will say 94.7 plus 0.752, add up, let's see, plus 4.5 and 0.011, and you get 99.963, which is close enough to 100%. 99.9 will do the trick. And so that would mean that these would actually add up to being about 1. So very good. Now you have solved it and checked your answer. to make sure that it at least makes sense. So that should give you an idea of how to solve those more complex isotope and average atomic mass calculations.